In this video, we will prove that the negation of if P then Q is logically equivalent to P and not Q. We know that two statement forms are logically equivalent if their truth values are identical. So we'll construct a truth table and demonstrate that the truth values for the negation of if P then Q are identical to the truth values for P and not Q. We begin by setting up the last two columns in the table first, one for each of the statement forms in the equivalency we want to prove. So one column heading is the negation of if P then Q, and the other column heading is P and not Q. Next, we represent each part of the two statement forms in one of our working columns. For the negation of if P then Q, we will need a P column, a Q column, and an if P then Q column. For the statement form P and not Q, we will need a P column, but we already have one, and we will need a Q column, but we already have that as well. So we only need to add the not Q column. Our columns are ready, but how many rows will we need for our truth values? Well, we have two possible truth values, true or false, and we have two statement variables, P and Q. To calculate the number of rows we will need, the base is the number of truth values, 2, and the exponent is the number of statement variables, also 2. So we will need 2 squared equals 4 rows. If there were 3 statement variables, we would need 2 cubed equals 8 rows, and so on. Since we do not know the truth values of the two statement variables P and Q, we must allow for all possible combinations of truth values for these two variables. To organize our table and ensure that we obtain all possible combinations, we enter true for P and true for Q in the first row. For the next row, we copy what we entered for P in the previous row, true, but we enter a different value for Q, false. So the first two rows do not match. However, for the third row, if we again copy the truth value for P, true, there is no truth value that we can enter for Q that will differentiate this row from the previous two rows. If Q is true, the third row matches the first. If Q is false, the third row matches the second. So it's time to change the truth value of P. In the third row, P is now false, and we maintain the pattern we established for Q in the first two rows, so we enter true. For the last row, we again copy the truth value for P from the previous row, false, but we enter a different value for Q, false, so that the last two rows do not match, and the pattern for Q from the first two rows is maintained. We now have all possible combinations of truth values for P and Q. Now we complete the remainder of the table. For the if P then Q column, we know that the conditional is only false when P is true and Q is false, and the conditional is true otherwise. So we enter false in the second row of this column and true for the remaining rows. For the not Q column, we know that Q and not Q have opposite truth values. So beginning with the first row, we enter false, true, false, true. And for the column representing the negation of if P then Q, we have the opposite truth values of the if P then Q column. So beginning with the first row, we enter false, true, false, false. Finally, to complete the P and not Q column, we AND the P column with the not Q column. Since statements with the logical AND connective are only true when both statements are true and false otherwise, beginning with the first row, we have true and false, which is false. Then we have true and true, which is true. And for the third row, we have false and false, which is false. And for the last row, we have false and true, which is false. In each of the 4 rows, the truth values for the negation of if P then Q and for P and not Q are identical. So the 2 statement forms are logically equivalent. Now we draw our conclusion. Therefore, the negation of if P then Q is equivalent to P and not Q.